Welcome back, everybody. So this is the second part of Chapter 4. In Chapter 4, Section 1, we talked about probability distributions, right? Which is basically just if I run a probability experiment, show me all of the possibilities of all the probabilities that you could have, right? That's a probability distribution. What we're going to talk about today is a unique type of probability distribution. It's called a binomial distribution. Prefix bi meaning two, right? So I'm going to be having to do like one or the other type thing, the two options. All right, so let's talk about what makes a binomial, right? When we talk about like a binomial in terms of a polynomial, that's like a two-termed polynomial, right? So it's got something to do with two, right? A binomial experiment is a probability experiment that satisfies the following conditions. 4 conditions for a binomial experiment. And there's going to be a couple questions on the quiz that say, okay, is this a binomial or not? Is this a binomial experiment or not? Almost. Oh, look, they're doing trig identities over there. They got sine squared plus cosine squared equals? Sine squared plus cosine squared equals?
1.
Yeah. We're doing it right now. Yeah, look, sine squared plus cosine squared over cosine. Oh, so that's 1 over cosine, which is secant.
Those make
Yeah, I
zero.
don't remember any of that.
It was like translating like differently.
Look at that. And I loved trig identities. They were actually kind of easy. Puzzles, like just
I love them when I can use the sheet.
yeah,
Look
really.
at them.
Where'd the numbers go?
All right, so a binomial experiment has 4 conditions. First condition, the experiment is repeated for a fixed number of trials where each trial is independent from the other trials. Independence is key. Let me ask you, based on that situation right there, was our M&M experiment binomial? Was our M&M experiment binomial? Was each trial? Oh, I'm sorry. I shouldn't have said that. That's a bad example. I was thinking picking one then the other. Did we replace? No. So each pull was different, right? I'm talking about like our pull then pull, right? But then we threw them back in to do the next trial. So that was a little weird. I shouldn't have said that. That was a bad example. Each trial must be independent from the other trials. Right? Each trial must be independent from the other trials. Second thing, and this is where it kind of gets its name. There are only 2 possible outcomes. Either you get a success or you get a failure. And it's important to define what the success and failure actually is. What is a success? What is a fail? Based on your scenario. Third thing, the probability of success must be the same for each trial, which kind of ties in to the first condition, right? If the probability of success was not the same, well, therefore then the trials would not be independent. They would be dependent on one another, right? If somehow the probability of success went up, well, then that's no longer binomial because it's no longer the same probability for each trial. And then the last one there, the random variable x counts the number of successful trials that you have. And that fourth condition is just kind of like setting us up so that we can use some calculations on it. Basically, things that you need to make sure. Independence and only 2 options. Success or fail. That's it. Binomial. Either you win or you lose. Actually, I shouldn't even say that. Either you win or you don't win. Because sometimes you can tie, which is a not win. Yeah. Either it happens or it doesn't, right? Black and white. No gray area, right? Only 2 possible outcomes. Success or failure. That is it. Okay. Some notation that we're going to be using within some of the calculations just to kind of set the stage here. And just like it always is the number of trials that are repeated. It said, I forgot to make note of this, but it did say for a fixed number of trials, it just can't be like an infinite number of trials. We can't just theoretically suppose that I could run this forever. We have to say, okay, we're going to run this 15 times. And it's necessary to say that because that's what goes into the calculation. How many times you ran this trial. The number of times the trial is repeated. We're going to have two letters representing success and failure, P and Q. P is the probability of success in a single trial. Q is the probability of failure of a single trial. And because it is binomial, P and Q are complements of each other. P and Q must be complements. If they are not complements, then this is not a binomial. They must be complements of one another. P is going to denote the probability of success. Q is going to be denoting the probability of failure. And then X is our random variable, which represents the count of the number of successes in n trials. Okay, X is going to represent the number of successes that we want in n trials. Excuse me. So again, just running through that. N is the number of trials that we use. So say we're going to run something 10 times, N is 10. Say a probability of success is 30%. That means the probability of failure is 70%, right? P would be 30%, Q would be 70%, 0.3 and 0.7. Random variable represents the number of times of successes in n trials. So if I say I'm going to run this 70 times, X is going to represent the number of successes I want in 70 times. Like, okay, if I want to know how many, what's the probability of me getting, 50 out of those 70 as successes? 50 out of those 70 as successes. 50 would be my X. How many times I want my success to happen. All right. So let's try to figure out if we can decide whether something is a binomial or not, based on those conditions that we have on the first page. The probability of flipping a tail of a weighted coin is 0.4. The random variable represents the number of trials flipped in 10 tosses. Binomial or not? Is it binomial or is it something else? Does it meet the condition of independence? If I flip the coin, I know it's weighted, but if I flip the coin 2 different times, does one affect the other? No. Okay, so this is independent. So it meets the meets the condition of independence. The probability, and I can jump now to 3. The probability of success is going to be the same, right? Because it is independent. Now, and is it a fixed number of trials? Did I note how many trials I was going to do? Yep. And lastly, our condition of, are there 2 possible outcomes? Yeah. 2 possible outcomes. Yeah. Flipping a tail and not flipping a tail, right? Not flipping a tail is otherwise known as flipping a head. But, think about this. What if it like stands on its side, right? We never consider that option, do we? But so in that case, we could say, well, it's not a tail, right? Whatever happened, it wasn't a tail. It either was a tail or not, right? So it is either a success or a failure. So therefore, we can call this one a binomial. All right, a jar contains 2 red, 3 blue, and 8 black marbles. You select 4 marbles from the jar without replacement. The random variable represents the number of red marbles chosen. There's several things that make this weird. Why is it not? The idea of replacement, right? It's not independent anymore, There's another reason, though. Good. Well, actually, no, that's not true. Represents red marbles chosen. Exactly. So my binomial piece of this is red or not red. Does that make sense? Even though there are other colors, my success is a red. What's my failure? not red. You know what I mean? Otherwise known as blue and black. You know? So even though there are different outcomes that I could possibly have, my success is a red, my failure is not red. Another piece about this that says, yeah, I'm selecting 4 marbles, but am I repeating my trials? No, I am not repeating my trials for a finite amount. My one thing is that I've done it 4 times, right? Maybe I need to select 4 times over a course of 10 different trials. You know what I mean? But really, the thing that stands out for not binomial is this without replacement. On a 20-question multiple choice test, there are 5 choices for each. You know nothing about the material, so you randomly guess on each question. The random variable represents the number of questions you get correct. Binomial or not? Why not? I think we are considering here that.
Is the guessing considered?
It's not like a.
Yeah, I call this binomial. I'm considering the 20 questions as repeated trials. Finite amount of trials, I have 20 trials. Because they are independent from one another, right? My probability of guessing correctly, does it change on each question? No, because I don't know anything about the material. And it's key to point out that I know nothing about the material. Because if I knew a little bit about the material, would the probability of success be the same on every question? No, I may know something more about question 15 than question 18, and therefore my probability of success might be a little higher, right? But if I know nothing about this, well, then I've got a 1 out of 5 shot for each of these questions. Now, you may be thinking, well, if this is a multiple choice test, then I've got A, B, C, or D. There's multiple outcomes, right? But wait a sec. What's my success? How can I define what a success is? Getting the question right. Therefore, the failure is getting the question wrong. It's not necessarily about what choice I choose. It's whether it's right or wrong. So we would consider this binomial. Yeah. All right. So if we can define something to be binomial, well, then we can actually use a fancy-dancy formula, which you guys don't need to memorize, but do need to decipher. This is what's called the binomial probability formula. Binomial probability formula. If you can say something is binomial, if you can say an event is binomial, over a fixed number of trials, everything is independent, only 2 options, then you can use this formula. Now, this is the portion of the formula that I would say that you should use. How does the first formula differ from the second formula? Isn't this piece the same as this piece? Right? I'm just kind of like writing out my combination formula in the second portion. The p to the x times q to the n minus x is the same. The only thing that's changing is the NCX, the combination formula. So let's kind of sift through what we have here. We have n number of trials, and I'm choosing them in x different ways, right? So basically that is saying how many ways out of the n trials could I get x amount of successes, right? Probability of exactly x successes. If I have n amount of trials, if I'm running 50 trials, and I want to know how many times I'm going to get 30 successes, I would do 50C30. That's how many different ways that we could represent 30 out of those 50. Right? Those are all the possible ways. Then I multiply it by p to the x. Now, what is p to the x? P, again, was denoted for the probability of success in a single trial, right? So if I know the probability of success is, 20%, I can say 0.2 to the x. What was x? The amount of trials I want successes in, right? So if I'm running those 30 trials, I would say my probability of success to the 30. Then I multiply by q. Now what is q? The complement of p, the probability of failure, right? So whatever 1 minus the probability to the, now look at the power there, n minus x. N minus x, the number of trials minus the number of successes, which makes sense because if I have n amount of trials and I want to know exactly x successes, how many are going to be failures? N minus x. So you're taking the probability raised to the power of that probability. What am I meaning there? Well, okay, the probability of success raised to the power of how many times I want that successes to happen, times the probability of failure to the power of the number of times that I'm expecting a failure. Okay? So how does this work? Let's take a look. I wrote this earlier on. Was it really still placed in the guidance? Yeah, right? I'm sure. Suppose Jose Ramirez has a 0.3 probability of getting a hit. Right? Suppose he has a 0.3 probability of getting a hit. Assuming that all at-bats are independent, which is a big assumption. Assuming that all at-bats are independent, what is the probability that he gets 4 hits in his next 10 at-bats? Okay, is this a binomial event? Either he gets a hit or he does not, right? Yes, there are other options. He could walk, he could strike out, he could fly it, whatever. But he either gets a hit or he does not. Okay? Is each independent? Yeah, I'm assuming that these are independent. Right? And the probability of success, therefore, is not going to change each trial. All right, so let's define everything that we have. Again, the formula was n, c, x, p to the x, q to the n minus x. Okay, what is n in this case? What is n? 10 at bats. What is x? How many times do I want a success to happen? 4. What's p? Which is 0.3. What's q, therefore? 0.7. The probability of not getting a hit. We have everything we need, don't we? Okay, so we can say, now, please understand, this is the probability of getting exactly 4 hits. Not the probability of getting at least 4 hits. We'll talk about that here in a second. But this is the probability of getting exactly 4 hits out of 10 trials. Order doesn't matter. That seems interesting there. Order doesn't matter. I am just saying 4 out of these 10 need to be a hit. Okay. All right, so let's plug it in and see. We've got 10C4 times 0.3 to the 4th. Q, I know what Q is, that was stupid. 0.7 to the what power? 6th. Notice here that these powers must always add up to what? N, right? 10 in this case. Yeah, those powers must always add up to 10. Okay, so let's run that number. Let's spoil it for us. Come on, buddy. Okay, we have 10. Oh, get back there. 10 C4, and then we're going to multiply by 0.3 raised to the 4th times 0.7 raised to the 6th. Oh, I need an extra parenthesis there. 0.2. 0.2. There is a 20% chance that out of his next 10 at-bats, exactly 4 of them are going to be hits. Exactly 4 of them are going to be hits. Okay. Is this the probability of getting at least 4 hits? No. This is the probability of getting at 4 hits. Exactly 4 hits. Different type of problem here. Rotator cuff surgery has a 90% chance success rate. The surgery is performed on 3 different patients. Find the probability of the surgery being successful on exactly 2 patients. I really liked this diagram and how the book showed it. So now I'm going to show the diagram and walk you through the diagram, and then we're going to do the formula to make sure that it matches. Take a look here. Is this a binomial event? Well, either it works or it doesn't, right? Either a surgery is a success or it is a failure. Is there a fixed number of trials? 3. Are they independent from one another? I think we are assuming independence. One surgery does not affect the other surgery. The success of one surgery does not affect the success of another surgery. All right, look at all the different possibilities that we could have. The first surgery is either a success or a failure. The second surgery is either a success or a failure. And then the third surgery is either a success or a failure. So we have all of these different options that we could have. So how many successes are there? Well, there's 3 here, right? There are 2 here. There are 2 here. There are 1 there. There is 2 here. There is 1 there. There is 1 there. There is none there, right? So find the probability of the surgery being successful on exactly 2 patients. Okay, so this first option is not what we want. This second option and the third option is what we want. And then this option here is what we want, right? So the probability of getting exactly 2 successes is this or this or this. When I say or, what operation should you use? Addition. So it's 81 plus 81 plus 81 all over 1,000, right? And how did we get that 81? Well, the probability of success is 0.9, right? 90% success rate. So really it's 9/10 times 9/10 times failure, 1/10, right? Or in other words, we can put that 1 anywhere. The multiplication is commutative. Okay, so 81 plus 81 plus 81 gets me 243. 243 out of 1,000. So 0.243, right? Now let's run our formula. Let's see if we get 0.23. Okay, what was n? 3. What was x? How many successes did we want to go for? 2. What's the probability of success? 0.9. What's the probability of failure? 0.1. Okay, so that means we would have 3c2, 0.9 raised to the second, 0.1 raised to the first, right? Okay, 3c2 times 0.9 squared, okay, times 0.1 raised to the first power, 0.243. See how that works? This is just a visual diagram of basically that exact same formula, which is interesting to point out. Look at this, 0.9 squared. Isn't 0.9 9/10? Isn't that 0.9 squared right there? Isn't 0.1 1/10? Yeah, 1/10. That's how. This is basically that calculation right here. Is 81 over 1,000. And then this is saying, well, how many different ways can we select that? We can select that 3 different ways. 3 times 81. Okay. All right. A standard 6-sided die is rolled 10 times. Find the probability of rolling exactly 3 4s. Find the probability of rolling exactly 3 4s. Now, I want to know exactly 3. Right? Exactly 3. Not at least 3, but exactly 3. What is n in this case? 10. What is x? 3. What is p? 1/6. I don't know why I put parentheses around it. What's q? 5/6. You follow me there? P is the probability of success, which is 1/6. Q is the probability of failure, which is 5/6. Anything other than a 4 is a failure. So we have 10C3, 1/6, 5/6. 1/6 is being raised to the third power. What's my power on 5/6? Seventh power. How many times we want a failure to happen? So we do 10C3 times 1/6 raised to the third times 5/6 raised to the seventh. Bingo. 0.155, 0.16. We have a 16% chance of getting exactly 3 4s. Exactly 3 4s. Okay. Find the probability of rolling exactly 8 numbers greater than 2 out of 10 rolls. Do I want to hold on a second? Do I want to do this one or do I want to jump to next? No, we can. I'll find the probability of rolling exactly 8 numbers greater than 2. Yeah, let's jump to the next one for the sake of time here too. This one. This is what I want to jump to. Suppose that 78% of Lake High School students like football. You randomly select 10 students in the school. Find P of 5. Find P of 5. Now this notation, that find P of 5, that is saying find probability as where X is 5. So in this context, I'm going to randomly select 10 students. P of 5 is saying find what's the probability of exactly 5 students out of those 10 liking football. Okay. Well, in this case, I would say N is 10, X is 5, P is 0.78, and Q is 0.22. Okay, so that means I want 10C5, and then I have P is 0.78, and then Q is 0.22, and they are actually both raised to the 5th power, right? Because the number of successes I want is 5, and I've got 10 trials. Got the power 5. So 10C5 times 0.78 raised to the 5th. Yeah, sure, whatever. Times 0.22 raised to the 5th, which gets me 0.037. I don't know my answers right now. 0.037. Now, if I take all of these probabilities, if I had said, find the probability of 1, 2, 3, 4, 5, I should have started with 0. Find the probability of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. What do you think they all add up to? 1, right? 1. The probability of the sum of all of these things, if I calculate the probability of 0, probability of 1, 2, 3, 4, all the way up to 10, all the probabilities together would be 1. So don't worry about this being small. That's okay. That's to be expected. I want to find the probability of exactly 5 students coming out to be out of these 10 liking football. Okay. We don't need to find P of 9. Let's find this. What is the probability that at least 2 of the students will say that they like football? So now let's change it a little bit. Let's say instead of exactly, let's find at least. What is the probability that at least 2 of the students would say that they like football? Okay, so what do I want to find the probability of? I want to find the probability of 3 liking football. Well, and 4, and 5, and 6, and 7, and 8, and 9, and 10, right? Because I want to know at least 2. Oh, and should I count 2 as well? At least 2. Yeah. So I know this full probability, the probability of being greater than or equal to 2 is really equivalent to the probability of 2 plus the probability of 3 plus the probability of 4 all the way up to the probability of 10, right? Now, I don't know about you guys, but I don't want to run all those calculations. Is there a simpler way?
Could you use the P instead of the C?
Oh, don't use, no, that's not it. Don't use the P instead of the C.
Other equation also pretty quickly told us not to use.
No, I wouldn't want to use that either.
Use the Q.
I think I hear what you're saying. He's like, use the Q, which I'm assuming you're talking about the complement, right? The opposite, right? Think about this. Isn't the probability greater than or equal to 2? You know, what if I did this? 1 minus the probability of less than 2. Right? Aren't these things equivalent? Now, is this thing easier to compute? Yeah. I could take 1 minus, well, this is the probability of 0 plus the probability of 1. Do I include 2? No, not or equal to. Oh, now that's a lot easier to find, right? So in this case, probability of 0 would be equal to, okay, I have 10, what did I say? 10 choosing 0. 10 C0. And the probability of liking football is, what did I say, 0.78? Yeah, 0.78. 0.78 raised to the 0. 0.22 raised to the 10th. And then I want to do that exact same calculation for P of 1. 10C1. 0.78 to the first, 0.22 to the 9th. Okay. Let's calculate both of those. 10C0, 0.78 raised to the 0, and then 0.22 raised to the 10th. Very small number. Okay. Got 7 zeros, so 6 zeros in front. 1, 2, 3, 4, 5, 6, 2, 7. And then I say, okay, probability of 1. I'm going to do that exact same calculation, but instead of 10C0, I'm going to do 10C1. Instead of 0.78 to the 0, I'm going to do 0.78 to the first. And instead of 0.22 to the 10th, I'm going to do 0.22 to the 9th. Okay, another really small number. 5 zeros in it. 1, 2, 3, 4, 5. 9, 4. Okay. So what am I going to do now? I'm going to add those two up. 0.6 zeros. 2, 7 plus 5 zeros. Okay, 9, 4. And then I'm going to say 1 minus that, which gives me 0.99. How many nines? 1, 2, 3, 4, 5. 5 nines. So we would say 0.1, 2, 3, 4, 5. There we go. Almost certain, right? Almost certain that if they chose 10 people, at least 2 of them would say that they like football. At least 2. Okay. Let's skip to this. Okay. Mean, variance, and standard deviation of binomial distributions. Mean, variance, and standard deviation. Mean, variance, and standard deviation is super easy to compute. It is extremely easy to compute. The mean of a binomial distribution is just n times the number of times the probability of success. Remember, mean is like expected value, right? Mean is like expected value. If I say I have a 0.3 chance of success and I'm running 10 trials, I expect to see 3 successes, right? If I've got 10 trials and my probability of success is 0.3, I expect to see 3 successes. N times the probability of success. That's our average. That's our expected value. Okay, for variance, all you've got to do is multiply by Q. You take your mean times Q. Okay, you basically take N times P times Q. And then for standard deviation, you just square root that. Okay. Again, all of these are on your formula sheets. Let me jump to mean, variance, and standard deviation. I got this problem here. It says, suppose the probability of the Browns winning a given game is 0.35. Way too high. That's way too high. Browns winning a game is 0.35. Losing a game is 0.64. And the probability of a tie is 0.01. Find the probability of 8 wins exactly 8 wins in a 16-game season. Okay, well, that would be 16C8. Probability of a win is 0.35. Now, what is probability of failure? 0.65, right? Because a win is success, a fail is not win, right? So we have to kind of like count tie in with the loss because that's not winning, right? So it would be 16C8.35 to the 8th, 0.65 to the 8th, right? And then we could calculate that out. Exactly 2 ties. Now, what do you think the probability of getting exactly 2 ties is? Super low, right? Yeah, so know what to expect. All right. In a 16-game season, find the mean, variance, and standard deviation for the number of wins. Now, if I've got 0.35 as my P, probability of win is 0.35. Probability of not win was, we said, 0.65, right? So that means my mean in a 16-game season, I expect to see how many wins? On average, 5.6 wins. Again, way generous for the Browns. All right. So then my variance, sigma squared, would be N times P times Q. Okay. 16 times 0.35 times 0.65, which gets me 3.64. And again, we don't really use variance much. We use standard deviation. So if I square root that, that gives me 1.91. So that's a standard deviation of 1.91 wins. So therefore, I can say that if the mean is 5.6 and my standard deviation is 1.91, how likely, rounded up to 2.79, how likely is it that the Browns are going to get an 11-win season? Extremely unlikely, right? Why? Because that is more than 2 standard deviations away from the mean. And I rounded it up to 2, 7.6, 9.6. Yeah, anything above 10 is highly unlikely. 3 standard deviations, heck, add another 2 on that. 14-game season? 14-win season? No way. That's more than 3 standard deviations away from the mean, based on this probability, obviously. Make sense? Mm-hmm. All right. I think I've sufficiently bored you. There's the homework. I don't know why it says homework 14. Must be from an old set of notes. Oh, I need to pass back a lot of junk. I've got just like a lot of stuff that I've been waiting for people to read in here. This is the chapter 3.